My world's so bright, it's hard to breathe, but that's alright. Hush.
Hey guys, this is Metacube, and today we'll be looking at the God program for our Qiskit algorithms. So, it kind of has nothing to do with like the quantum application of this, but it's rather just for our peace of mind, and it just makes running quantum algorithms so much easier. So, this is the code, and I will have a link down to this in the description where you can just download the file and use this. Yeah, so I'm just going to be giving you a step-by-step overview of what this is, and as I go along you can type it, or as I said, you can just get this text from the description. And yeah, let's just get started. So what I do with this function is I just copy this function and then paste it at the beginning of any Qiskit program so far that we've covered or that I've done, so that I don't have to worry about importing everything. And especially for running the program, as you'll see, this whole program makes it so much easier. So as always, it starts off with import Qiskit. It's kind of fundamental. And then from Qiskit import all. Then from Qiskit.tools import job monitor. And what this allows us to do is when our job is running on an actual quantum computer, so let's say like IBM Valencia, here it'll tell us if the job is still pending, or if it's getting verified, or if it's currently running, and if it's finished. Then Qiskit.visualization, this allows us to use the plot histogram feature so it can make the bar graph, and the plot block multivector, which is very nice for looking at states and visualizing them. And lastly, this isn't required, but I like to import NumPy as NP, because if I have to do some uh, number crunching or some other calculation, I can just throw this on there and just do NP dot whatever function I want. And then lastly, this is the mitigation part, and this is just something I've been messing around with. So I've commented it out. That means that you guys don't need to um, actually type this in. If I add it on, then I'll tell you guys in a later video. But yeah, you don't have to type in any of the stuff that's commented out. So yeah, this one is just optional. I would not do this if it's for some reason. Sometimes it doesn't compile properly. I guess they must have updated this or something. But yeah, if that happens, just comment this line out, or just don't even write it and just move on. So now, this function is going to be called run underscore program. So pretty simple. And what we're going to pass in as the inputs is going to be our circuit, the number of qubits our circuit needs to run. So if we could C equals quantum circuit 3 comma 3, that means it needs 3 qubits to run. So we would do 3, and then we would say the number of tries, however many iterations you want to run that program, and then type of comp. So this is pretty important. This is what's going to decide what computer is this going to be running on, basically. So if we type in qsim right here for the fourth parameter, we basically are going to be getting sim backend is equal to air.get underscore backend, and then chasm simulator. And this is going to make the program run on the quantum simulator that IBM has provided with us. So before all this, remember, we have to load our account. So to access anything from IBM, we have to load the account. So if you remember in the first program where I taught you guys, the first video, sorry, of how I taught you guys to access your account and take that PIN number and put it in. Once you've done that, you just have to press load account, and it should work perfectly fine. And once you've loaded your account, here we have certain if statements. You can also do switch case. Once I get some more conditions, I'll probably just turn this into a switch case. But yeah, for now, this is fine. And basically, we have the Q simulator, and this part just tells the backend to use the chasm simulator and then execute our job, and then it's going to return the job.result. So it returns a result. That's great. Next, if we want a state vector, if you want to look at that plot block multivector state of the qubit, we just put state vec, okay, and the double single quotations really doesn't matter. And then we put the sim as error.getBackend, which is the same as this one, except we put state vector simulator, and that's all good. And then we just return, we tell the program to execute circuit, and then we say the backend is equal to sim backend, which is what we initialize here, and then dot result dot get state vector. So that part of the program is going to return state vector. Now, this is the reason why I made this program. So basically, I made this program a couple months ago, and like half a year ago, approximately. And what happens is back then there wasn't that many people using the quantum computers. So here I decided that in the future, as the quantum computers gain more traffic, it's going to be a pain to sort out which quantum computer currently has the lowest amount of pending jobs so that I can get my program to run the fastest instead of waiting in a huge line. So normally you would have to either manually check them one by one, or you'd have to go to IBM Quantum website, check all the programs running, blah blah blah. It's just a hassle. So what this program does, or what this section does, is basically it automatically checks which is the lowest amount of pending jobs and just sets that as your computer that you want to run on. So here we say provider is equal to IBMQ.getProvider, hub equals IBMQ, standard stuff. And then here I set the pending jobs as default to 1,000. So we start off at like a really high number that we just want to get lower. And you can change this if normally the computer starts getting more than 1,000 jobs running, you can just set that manually higher. This just needs to be a really high number. So then we have an for loop and for backend in provider.backend. So provider.backend is a whole collection of different computers that IBM has, like IBM Valencia, IBM, none of the other ones that come off the top. But when we check, I'll show you. So then here I have a try catch or try except statement, and we have if or we're setting the qubit count is equal to the length of backend.properties.qubit. So first, this is checking if the backend has enough qubits for our job. So we need at least the number that we put for qubit num. Okay. So if the backend.status.pending jobs is less than pen job, okay, so this is the pen job. If it's first less than 1,000 and its qubit count is greater than or equal to the qubit num that we desired, then we say pen job is equal to backend.status.pending jobs. So this is the current job. And then current comp is equal to backend.name. So we save that backend and be like, okay, this is the lowest one. This is our program will have wait in the shortest line on this computer and basically save that. And then amount of qubits is equal to qubit amount. So we just put we just save the amount of qubits in another value. Okay, and this happens over and over again. And as long as there's another computer that has the number of pending jobs less than this pen job and its qubit count is greater than or equal to the one we need, it will basically set that as the new current comp. And then we do an exception because sometimes it catches on I think the quantum simulator. So it sometimes tries to do that on the quantum simulator, which doesn't have any qubits. So we just do except. I know this is um, bad styling, but yeah, I just needed something that works. So then this is where it shows us what computer we chose, or the program chose. So it prints out the current comp, its name, and then the pending jobs, so how many jobs are currently in front of you. And then available resources is how many qubits does it have. So then now we set the backend is equal to the provider.getBackend current comp, so that was the name of the computer that was saved. Then we say job is equal to executes, and then we input our circuit, the backend equal backend, and then shots is equal to number of tries that we initially requested for. And then we have job underscore monitor, and then input the job as a parameter. What this allows us to do, once again, is it takes this thing that we imported and basically it shows us when our job is running, when it's getting validated. Just gives us more up-to-date info on it instead of us just waiting, just thinking if our program ever ran. And then after all this, and returns job.result. Once again, this part is for the mitigation algorithm. I've been tweaking with it, and what happens? It's not working. I think they had an update or something, and suddenly it kind of crashes. So I'll just be looking into this, messing around with it. Yeah, if this gets fixed or I find a way to do this, I'll update the file. So basically, that was the whole function. And let's test this out first. So run this, and now I will run this. So this is an example of the bar graph, and right here I've made a quantum circuit that's 1 1, right? And I've done a Hadamard on the 0th bit, or sorry, that's like the first bit, and then I'm measuring this first bit, and I'm setting a qubit, and then I'm setting it to the first bit. So now I want to plot histogram, but instead of doing this whole manually running the program, I can just make this function at the top, and then I just put run program C because that's our circuit name, 1 because I only need a max of 1 qubit, and then 5,000 tries, just put that there, and then here, what is interesting is that since I was going to be running the probably on a real quantum computer more often than not, I just set this as like the default case. If I don't enter anything for a type of comp, um, or I don't even put in a value, like if I just give it a space, anything other than chasm simulator or state vector simulator, um, it'll just run it on a real computer. And then we say get counts, and then we run this. You're gonna get this warning. It doesn't really mean anything. It just says that your account is already in session and it's just going to replace it, which is fine because it's only going to be running. So now, as you can see, IBMQ ORENTs. So it had 0 jobs, so we're first. Available resources 5 qubits, that's plenty. Our job is actively running, as you can see, and that's updated live. So we are not left in the dark. And now we just wait and see it says job is successfully run. And now we get about a 50-50 didn't run, which if we remember, H was in or the first qubit was in superposition, so half the time it will measure out to 0, half the time it'll measure out to 1, so it's good for us. So now, let's say I wanted a bigger program. Let's say I needed to have a minimum of 7 qubits, okay? And let's see what this does. We don't need 7 qubits for this one, but let's say I wanted 7 qubits. I wrote a different program. Let's see how this runs. So, okay, we might not do this, but as you can see, IBM Q16 Melbourne, 543 jobs. Okay, and its available resource is 15 qubits. The job is queued, and yeah, that's why. Let me just stop this real quick. Yeah, so you just get an error if you stop it in the middle. But yeah, let's just make this look clean again, please. So yeah, as you can see, 543 jobs. Yeah, so instead of manually searching for whichever one had the least, I can just easily run this program. And while this is running, we can move on to this one. So here, as you can see, I'm looking at the state vectors of these. And for this one, I can still use run program. And let's take a look at our quantum circuit. So let's finish running. And there's always going to be that error. So right now it's slightly imbalanced, but hey, it's a real world. Not everything's perfect. So now, I have 4 qubits and 4 bits. I perform an X operation, so a not flip on the first qubit, or 0th qubit, Z flip on the first qubit, and a Hadamard on the second qubit. Okay, so I've commented this out, and I'll show you guys why later. But here I have C. The thing is, I don't need any qubits for this because this is going to be running on this other backend, so I don't need to actually compute this. And I need to 0 tries because it's just the state vec. And I'll just put state vec right here. Now, a shift. Yes, the IBM factory thing, we get that warning. And as you can see, we have a not flip on this one. We have Z flip, which kind of does nothing to qubit at 0 because they all start at 0, remember? And okay, there's a Hadamard gate right here. And so this is pointing in the X direction. And then we didn't do any operation on this qubit 3. So it's all good. Now, just something that's interesting is if I take this off and instead I perform a CNOT gate from 2 as the control qubit and 3 as the target, something interesting happens. Since those two qubits are now entangled, you basically don't see them anymore. Ooh, quite literally spooky action at a distance, I guess. So yeah, this just makes life a whole lot easier, and Chasm Simulator works the exact same as this one. It's pretty simple. And yeah, so in the future when I'm running my quantum programs, I'm always going to be using this function. If there are any updates to this, I'll let you guys know. And thank you for watching. Please like and subscribe if you enjoyed the video, and stay tuned for more quality content.